Okay, hello, Modern Robotics class student. Uh, Today's class is 14th week. Actually, it will be our final official class because we are having the final exam in the 15th week. So this class will be substituted by final exam. So today's class is our last class. Actually, we already fixed our schedule about final exam. So the final exam time is Thursday, next Thursday, 4 to 6 p.m. So as I already told, our class, our final exam will came out from the exercise chapter 3, 4, 5. So I already uploaded the solution of exercise 3, chapter 3, 4, 5. So I hope you study using that material. So let me review a little bit. So in chapter 3, we deal with the rotation matrix and exponential coordinate and the large SO3 and small SO3 things was done in chapter 3 and homogeneous transformation matrix. So actually, the midterm exam is overlap in this chapter 3, but some of problem will came out here. And next chapter was chapter 4. And in this chapter, we usually deal with forward kinematics. So forward kinematics, by making forward kinematics using screw axis. So that is the key point in this chapter. So you might familiar with this screw axis forward kinematics. So that is important thing in this chapter. And then chapter 5, we deal with Jacobian and velocity kinematics. So the Jacobian things will be came out here. So you might familiar about that. And actually, we skipped about statics. The statics is about in chapter 5, there is statics. In Korean, there is 정역학. So the stationary, some physical interpretation. So that is statics. So in statics, we deal with the relationship between torque and force. So let me briefly explain about that. Where is statics? Okay, about statistics, I will explain in this chapter, in this class. So you might also familiar with it. So in the statics, we usually Jacobian, and using the Jacobian, we can transfer the force to the torque. So that kind of things will be statics. So you have to uh, know about the statics in here. So today's class is about the last class of dynamics. So I will summary briefly. So in the previous class, we learned about the dynamic equation for single rigid body. So actually, the equation was very, very complex in the Newton-Euler formulation. But that equation was very simplified and symbolized. So as a result, the final equation having very simple formation. So that is the power of robotics theory. So in here, the force is the force things is step with the moment and force. So this is rotational things, and this is a linear things. And also the spatial inertial matrix also constituted by uh, rotational inertial matrix and mass. And we learned about the new concept of small earth joint. So there was large earth joint and there is small earth joint. So this one is Lee bracket of twist V. So using this concept, actually we can make this kind of matrix. Actually, this one is 3 by 3, and this one is 3 by 3, 3 by 3. So this matrix actually 6 by 6. As you already know, the adjoint T is also 6 by 6 matrix. So in the matrix formation, the matrix shape is same in the large adjoint and small adjoint. And then, yeah, this one is single rigid body and an equation. So by using this one, we will learn about multi-body rigid body dynamics in this time. Before before doing that, I want to introduce about the wrench concept. Okay. Actually, this is about the statics. Yeah, this one is very, very closely related to the statics. So in the wrench concept, we already learned about this one, like this one. And this concept is spec of moment and force. So wrench is the concept to represent moment and force together. So actually the torque we are familiar with expressing using capital T. And this torque equal moment arm length multiplying force F. So this one is torque, and the torque have the unit in the SI unit, Newton meter. So the torque T equal moment arm length multiplying force. More general expression about force and torque is wrench. So in the wrench, I already expressed the moment and force expressed together. So this one is 6/1 vector. And some, in other words, we call this one as 6-dimensional spatial force. So the spatial force equal wrench. So the wrench is more general expression to expressing moment and torque. And the moment and torque was merged in a single vector. Because we are using twist, the concept of twist, the spatial velocity, we can make also spatial force. So the important thing is if some wrench is expressed on the A frame, how can I define the wrench which is expressed in the B frame when we are know homogeneous transformation between frame B and A. So in this figure, there is A frame here and there is B frame here, and the relationship is the forward kinematics relationship is expressed in the TAB. And there is one point here, and this point is expressed by RA using A frame and RB using B frame. So there is a force F in R point. This force is one force, but when we expressing this one in A frame and in B frame, this actual value becomes different because the base frame is different. But the power or work, in the concept of power or work, the numerical quantity of power and work will be same without depending on the A frame or B frame. So the power or work or energy kind of things is not changed depending on the frame, base frame. So we will use this kind of concept. So the power can be calculated by spatial force multiplying spatial velocity. So spatial force is wrench and spatial velocity is twist. So wrench multiplying twist becomes power. And this is independent on the coordinate system. So this value in B frame and this value in A frame is equal. And because the twist having the relationship using large odds. So using this concept, we can input this value in twist A, and this one become like this. And if we take the transpose of this matrix, then this position is changed. This two position is changed, and we add T transpose here and transpose here. And because this value, this is same with this one, and then this becomes same with this one. So we can conclude this relationship. So as a result, if we want
transform the wrench in B frame to A frame, we can use a large order joint with the transforce. So actually, the twist case, we use A here, B here, A here, B here. But in the case of wrench, the position is changed. B here, A here, B here, and A here, and transpose here. So this one is a little bit different thing, but you might memorize this one as a official equation. So this one was about the more detailed concept, the detailed things of a wrench. Actually, the static things is about the torque and force. This one was not came out here, but let me check. Okay. Statics is very, very short in our class. So actually, the statics can be calculated by this equation. So let me briefly explain about statics. Let's use this one. Okay. Similarly, we use the concept of power. Actually, we learned about the power is multiplying of spatial force multiplying spatial velocity. And also, we can calculate the power using torque with the rotational velocity, theta. So, using the relationship between twist equal Jacobian multiplying theta dot, we can make this equation. So finally, we can conclude this one. So torque equal torque T can be calculated using Jacobian transpose with the spatial force. So this one is also an official equation. So you might memorize this one. So when we know the force, spatial force, some point, we can, in the statics, we deal with this kind of things. Oh. If there is some kind of this link, and if there is some force, if we want to know the torque here, we can, if we know the joint Jacobian, we can calculate the torque using Jacobian and the spatial force to maintain this force F. So these things will be about the statics. So I will just briefly explain about this one. And now we will focusing on the dynamics. Okay, the Newton-Euler inverse dynamics. So we learned about the single rigid body dynamic equation, this one. By using this one, we can also construct multi-body dynamic equation. So if there is series link, open chain link, there is n link from 0 to n, and the reference frame is located on the center of mass of each link, here, here, here. And the basic link is ground, actually ground. And the n+1 link is on the end effector or tip. So in this case, we will calculate the inverse dynamics using Newton-Euler formulation. In Newton-Euler formulation, we are having forward iteration and backward iteration. The forward iteration is to calculate the velocity information, velocity and position things, and acceleration things is calculated from base tip. So this one is same with the previous concept of Newton-Euler formulation in the intelligent robotics things. So we are calculate from here to end the velocity and acceleration, and then backward iteration, we can calculate force and torque from tip to base. The reason we doing like that is when we calculate the speed, we have to know the ground speed. Actually, the speed is some kind of integrated concept, integrated value. If you are sitting in the metro train, even though you don't move inside the metro, if the metro train is moving, you are having some speed based on the earth. So when the base frame is changed, you can have different speed value. Similarly, if the base speed is changed, your global speed is changed. So when we calculate the speed or acceleration, the important thing is about the ground speed. So we start from here to there. And because the reason we use backward iteration, when we calculate the force and torque, if we know the acceleration things of each link, we can calculate the force or torque of each joint. But in case of there is some external force or torque which is exerted on the tip, if this one is 0, if this one is 0, it's okay. But if there is some kind of value like non-zero value, then this force is propagated from here to ground. So this is the reason we use backward iteration to calculate force. Actually, the speed on here, if the speed is 10, and if the tip speed is 100, in this case, this value does not affect this velocity. But so if this velocity is changed to like 200, even though this speed does not affect this speed, but if this speed is increased, this speed will be changed like that. So this speed affects this speed, but this speed does not affect this speed. So the velocity is forward iterated. Similarly, the force in this force affects this affect here. So using this concept, we will have two kinds of iteration process. Firstly, in zero position, we have the configuration of m, I, comma, j. So this symbol representing the configuration of j in I. So the base is I and target is j. So this one is representing the configuration. If the I frame is equal to 0, then we can express like this. In the case, we can just ignore this 0 value. So we simply write down like this. So if the base frame is ignored, we can assume the base frame is 0 position, 0 frame. This is for simplification, and this m0 comma I equal m0 comma I minus 1 multiplying mi minus 1 I. So if we move this matrix here, then this one is inverse matrix, and then this and this 0 index can be ignored. So we can simply write down like this. So some arbitrary I minus 1 comma I configuration, that means from I minus 1 to I, based on the I minus 1 to I, this configuration can be calculated using inverse of this one and this one. So this configuration actually expressing this one, because this one is inverse, and then go from 0 to here again. So actually you can similarly think this kind of vector calculation. When you calculate this vector, we can use this vector plus this vector. Similarly, this configuration is multiplying the inverse of mi minus 1 and then mi. So this one is one of the equation to express multibody dynamic equation. So just remember about this one. And then there is TSV. TSB is homogeneous. Similarly, the homogeneous transformation from S to P, S frame to P frame. We are familiar with this relation. The twist of S equal twist S and twist B, having this kind of relationship between using Odd joint, large Odd joint. So if we changing this symbol S and B, then we have to move this one to here. Then we have to use the inverse of Odd joint. Actually, okay,
Wait a little bit. Let me check this equation is right.
okay, this one is right. So screw axis for, okay, this one is about the twist and space twist and body twist. And this one is large Odd joint. This one is previous symbols. So let me a little bit change the style by using the symbol A symbol and S symbol. So A symbol is representing body screw and S symbol representing space screw. So this one is space twist or space screw. So we can substitute twist, space twist using this one, and the body twist changed by this symbol. So we can make this kind of equation, and TSB was substituted MI. Actually, MI is equal M0, I, and this 0, is just ignored for simplification, and we added inverse here. So this one is one more equation to memorize. The body screw equal Odd joint MI inverse SI. This one is one more equation to memorize. And then we have to define T I minus 1 to I homogeneous transformation matrix. Actually, this one from I minus 1 to I, which is relative transformation, previous link to next link. Actually, when we learn about each parameter, we constructed this homogeneous transformation of some A alpha D theta parameter. Using this parameter, we constructed some formation equation about this one. Okay, let me think about this one. if we change these two value, we can take inverse here, and the t I minus 1 to I transformation itself can be represented by these two things. So actually, this homogeneous transformation is relative transformation from I minus 1 frame to I frame. So when we expressing this largest C transformation, we can use T I minus 1 comma I. And this one can be calculated using the zero position configuration. Zero configuration from I minus 1 to I. And this one is relative transformation. Relative transformation. So we use body screw and theta I. So in this figure, this one is I minus 1 link and I link. If there is some rotation theta I, we can make the homogeneous transformation matrix between I minus 1 to I using this equation. So if we take the inverse of this one, then we can use transposition and then inverse here, like inverse like here, and we can take inverse here, and the inverse become minus in the exponential coordinate. So the reason we using this concept will be explained later. So basic things was prepared. Actually, the three equation was this one and this one and this one was some basic material to construct open chain dynamic equation. So we will use this kind of relationship to make Newton-Euler dynamic equation. So let me think some I link and I plus 1 link here. And in I link, there is length from I minus 1. So you might imagine there is I minus 1 link, and here also there is F range I, and this range I is action and reaction. So this one is some kind of internal force, and this one is propagated from end to base. And this force is same but different. Same value but different signal. Same but reverse direction. So this one came from this wrench I came from here, and this one is I joint and I link. And the center of I link, there is twist and twist dot. So this one is velocity term and acceleration term. And there is also I plus one joint. In I plus joint, there is length I plus one, and this length I plus one having the relationship of Jacobi other joint transpose. Okay, let me review this concept. Actually, in the length here, we learned about this equation. Yeah, this is one more equation to memorize. So when there is B frame and A frame, if the frame is changed from here, B to A, then we have to use BAT transpose. So using this relationship, we can construct this relationship. So let me rewrite F A length B order joint T B A transpose. So if we know length I plus one, and we want I plus one in the I this one is I. So we can use other joint T I plus one transpose, and we have different direction. Actually, this other joint means changing of reference frame from I plus one to I, and then we have to take the minus value because the different direction because of this one is action and reaction. So it becomes like this. So this one and this one is not the same one, but actually we can express like this. F I range I plus one expressed in the I plus one frame. This one is F range I plus one expressed in the I frame. And this one is having different different direction, so we add minus value. So this one and this one is action and reaction, and also changing of reference frame to calculate the equation in the I reference frame. So when we calculate some vector equation, we have to one base reference. So this value is having reference on the I plus one. So we change it, the reference to I, like this. So the twist I is body twist, and length spatial force is ice range based on the frame I. And GI is spatial inertial matrix of link I expressed in the frame I. So in the forward iteration, we can calculate the twist and derivative of twist using this equation. So memorizing this equation, So this one is body screw and Seira dot. So this one is I-link rotation. And plus this one, because the velocity is propagated from I minus 1, I like this forward direction. The previous velocity is added here. And the previous twist velocity is changing the reference frame using odd joint. So because before I already explained all the vector calculation should have same reference frame. So this value also change the frame reference frame to I minus 1 to I. So this one is velocity twist equation, and if we take the time derivative, we can get this equation. This one is time derivative, and using the chain rule, time derivative this one first, and then time derivative this one secondly, and this equation, the time derivative of odd joint, large odd joint. This one can be calculated like this. This term is calculated like this. In here, the other joint actually this one. And if we take the time derivative rotational matrix, we can get like this. And this value also can be calculated like this. And then if we simplifying this matrix, we can get this matrix. And this one is same with the small odd joint with this one. And this value is actually this one. So we can get the final, this one is also odd joint here. So these two things is multiplied here, here, and here. So it becomes twist I. So twist I here, here. So finally, we can get this one. In here, they substitute this one and this one. The position is changed. So this position and this position is changed, and then this minus value is deleted. So this relationship came from actually that concept came from the Lie bracket concept. Actually, Lie bracket is cross product of two twists. Actually, in the angular velocity, if we calculate this one is cross product of angular velocity, we can substitute it, this one as like this, as skew-symmetric matrix. So this cross product calculation becomes just matrix multiplying vector using the skew-symmetric what? If we change the formation of this vector to the skew symmetric formation, then we can make this kind of cross product calculation to the matrix multiplying calculation. Similarly, this one is 3 by 1 vector, 3 by 1 vector, and this one is 6 by 1 and 6 by 1 vector. So if we want to calculate this kind of more general 6-dimensional twist cross product can be calculated by this Lie bracket. This one multiplying this one. So this one is 6 by 6 matrix, and this one is 6 by 1 vector. So by using Lie bracket, we can make the cross product to the matrix multiplication. So actually, you can think the Lie bracket is the some kind of expanded concept of skew symmetric matrix. So by returning this, so if the calculation order is changed, then the plus minus signal is changed similarly to the cross product. So this one becomes like that. So final equation of acceleration term, actually spatial acceleration, because this one is spatial velocity, this one is spatial acceleration, becomes this equation. So this one is, the interpretation of this term is joint acceleration by theta to that. And this term is I minus one acceleration I minus 1 link acceleration in expressed in I link. So this one is changing of the reference, and this one is velocity product term. As you already saw, this one is some kind of production of two twist value. So this one is actually velocity product term. So from here we can get the centripetal or centrifugal acceleration or the Coriolis velocity. So the next one is backward iteration. In the backward iteration, we calculate the spatial force using already calculated spatial velocity and spatial acceleration. So the spatial acceleration term, the spatial velocity term, and a small other joint and spatial inertia, and the propagated force is some. Actually, this term is from this one. This term is from this equation, the single rigid body dynamic equation. This one is same with this one, and in the case of some I link, we saw there is spatial force here, and there is spatial velocity and spatial acceleration, and this term. This one is propagated from the I+1 link. So actually, F equal MA, so more general multibody term is sum of F equal MA. So MA is this term, and sum of F equal Fi minus other joint Ti plus 1 comma I transpose Fi plus 1. And this term is moved to other side here, so it becomes plus value. And finally, this equation is came out. So this one is resultant equation to calculate inverse dynamics. So by summary of this process, firstly, we have to choose the base frame, 0 frame, and frame 1 to n. So 1 to n is located on the center of mass of link. This is important thing. And n plus 1 become end effector position. And configuration of I minus 1 in I, which is theta equal 0, is needed because we will use this one okay, in somewhere. This one is also needed. And then this one is screw axis, which is I joint expressed in I. And this is a spatial inertial velocity, spatial inertial matrix of I link. And this one is spatial acceleration in 0 base frame, which is basically set. This one is 0, 0, 0, and 0, 0 minus g. Actually, this one is 6 by 1 vector. So this one is gravitational acceleration constant. Yeah, this one should be 3. Okay. And then this one is range spatial force on the tip. If there is this force, we have to define this one first. And this one is preparation to calculate fold and backward iteration. And if we know this information, we can calculate fold iteration using this equation. And in here, we have to know Ti to I minus 1 to calculate this kind of things. And these things is calculated by using this equation. And then by doing this, we can calculate velocity and spatial acceleration. After that, we doing backward iteration from n to 1. So in here, we already know the information about this one and this one. We can calculate this one, and finally we can calculate the torque by multiplying body speed. So this information becomes the inverse dynamics equation, which having this kind of form. So in the inverse dynamics equation, there is M matrix, the mass matrix, and mass matrix is multiplied with acceleration, joint acceleration term. And there is C term and G term. And C term is centripetal or Coriolis acceleration term. And this one is gravitational force term. So if we know the inverse dynamics equation, then we can change the position, and finally we can get the theta 2 dot using this equation. So in this equation, we have to know the torque and the environmental spatial force, which is applied to the tip, which is applying the tip. So using this information, torque, theta, theta dot, we can calculate theta 2 dot. This concept is forward dynamics. So actually, I already explained about this one. This theta 2 dot will be used to simulate some kind of rigid body motion by integrating this acceleration. So, if you are making some simulation program, you can integrate this value like the first order Euler iteration method. This one is if you calculate the forward dynamics and you can get, if you get the velocity or acceleration things, then you can integrate like this. So if you already calculated theta 2 dot, and then you can use this equation. So step time delta t uh, is a time step, and delta t multiplying acceleration plus velocity, then this is updated to the new velocity, and new velocity, the position is integrating the velocity and previous position. So this is basic integral method, the first order integral method. So by doing this, you can calculate theta and theta dot. Things more precise, more precise and accurate integration method is also the longitudinal method. So if you want more precise or accurate results, you can use this kind of high order integration method. And this method is not detailed, is not explained in detail, but just for reference, you can keep in mind the longitudinal method. And also in the simulations thing, there are many simulation engine named ODE or Blip or Vortex or something like that. And okay, the inverse dynamics things is done. Actually, let's take a break in here.